So the next speaker is Bastian Schlag, and he's going to talk about the ACTS vertexing and the deep learning vertex finder. And you have 15 minutes. You can start if you want.
Perfect. So you can see my slides?
Yep.
Perfect. All right. So, well, yeah, thanks. I'm going to be talking about ACTS vertexing and also some current and ongoing developments within the vertexing of ACTS, including some first steps in the direction of deep learning vertex finding. I'd like to start with a really brief introduction into what ACTS actually is. I strongly recommend the ACTS talk by Jiao Kong in recording session 6 if you want to have further details. So ACTS is a detector independent track and vertex reconstruction toolkit. It's based on the Atlas track reconstruction software, which has been tested extremely well over the last years, but it's roughly 15 years old and was not designed having multi-threading in mind at all. So ACTS is written in modern C++ with a thread-safe design, with const correctness and stateless algorithms. We really try to minimize the usage of virtual inheritance, and wherever it's possible, try to lift all the work to the compiler instead. We also try to keep our external dependencies really at a minimum level, meaning that currently we're only dependent on the eigenmath library and the ACTS core. Yeah, and our entire development is unit and integration test driven. In order to allow for also external contributors or contributors from outside CERN, we just recently moved from GitLab to GitHub, and you can find our repository here under this link. So feel free to check that out if you're interested. Coming to the vertexing in ACTS, so quite some work has been done here. Several Atlas primary vertexing algorithms have been re-implemented in ACTS and also numerically validated with respect to the Atlas physics performance. Here on the right-hand side, you can see a list of all the files and classes the ACTS vertexing suite is currently comprised of. ACTS offers some vertex finders, which you can see on the left-hand side. We have an iterative vertex finder and the adaptive multi-vertex finder. The first one was used in Atlas Run 2, and the second one, the adaptive multi-vertex finder, will be used in Atlas Run 3. And in fact, even this very ACTS version of the adaptive multi-vertex finder will most likely be used in Atlas Run 3. Then we have a set scan and a Gaussian track density vertex finder, both of which you would probably want to use as some kind of seed finder, since they return always a single vertex at a time. Then the ACTS vertexing has, of course, also some vertex fitters, namely the full Billois vertex fitter and the adaptive multi-vertex fitter, and of course all the associated utilities you need, like track linearizer, impact point estimator, and so on. The ACTS vertexing, of course, complies with the ACTS coding guidelines, meaning it's written in modern C++ with a thread-safe and modular design. It's very well documented for increasing code maintainability, and it's also extremely easy to set up and use. I have an example in the backup if you're interested, where I set up and use the ACTS vertexing in less than 40 lines of code, so that's pretty easy. In terms of performance, I'd like to show you some comparison plots against the original Atlas implementations, which, as I've already mentioned, have been tested extremely well over the last years. So I have some comparisons on pileup 60 GTB events. As you can see on the left-hand side, the difference in number of reconstructed vertices shows perfect agreement, and also on the right-hand side, out of all more than 35,000 reconstructed vertices in this case, all of them have perfect agreement in the number of associated tracks to the vertices. In terms of vertex position, on the left-hand side, you can see, also again tested against the Atlas AMBF version, the set position of the found vertices. As you can see, we have also really good agreement here on micrometer level. And regarding CPU performance, on the right-hand side, you can see a significant speed up with respect to the original Atlas implementation, even though no algorithmic changes have been made yet. Of course, we want to do so in the future, but for the time being, we have not made any algorithmic changes only. So these speed ups really come from optimizing the code and writing good code basically. All right. Next, I'd like to talk a little bit about current developments that are ongoing in ACTS. The first one being a generalization of track linearization. So the current track linearizer in ACTS and Atlas assumes or is based upon the assumption that you have a helical track model, which is of course not always the case. And with the ACTS propagator, we do in principle have all the information we need for linearizing tracks without assuming any underlying track model. This will then of course make the vertex filters more robust in all detector regions and could therefore harmonize primary and secondary vertexing, having a common math kernel. And since time propagation is fully integrated in ACTS, this will then also allow vertex fitting with timing information. The next development I'd like to talk about is a Gaussian track density seed finder on a grid. So as I've already briefly mentioned in the ACTS vertexing overview slide, we already have a Gaussian track density seed finder fully functional and working in ACTS. The problem with this, however, is it's extremely hard to cache track density values if you want to do so, because you're dealing with continuous track densities. And so what I've been working on the last couple of weeks, actually I tried to take this approach, which I will come to in a second, and put it in a grid, on a grid instead, in order to be able to make it faster. So the idea is the following. We model each track as a two-dimensional Gaussian distribution in the D0 Z0 impact parameter plane. You can see this on the right-hand side as a small example for 3 single tracks. And in this case here, we represent each track as a Gaussian density grid, actually. And since we are really only interested in density distributions along the beam axis, we can really only calculate the track contribution along the beam axis of every single track. So this would be the red part on the right-hand side in the example, meaning that for every single track, you really only have to calculate a one-dimensional vector. And so you can then superimpose all the tracks and just find the maximum along the beam axis, which you would then just call your vertex seed candidate. And this can be extremely fast in iterative approaches, where you iteratively always remove a single track or just a couple of tracks from your seed collection. Because what you can do then now, in your very first iteration, you would just calculate all these track contributions, all these one-dimensional vectors. It would just cache them, and once a seed is removed from your seed tracks, you can just remove this one-dimensional vector from this overall beam axis density vector. And this is extremely fast, as we will soon see, but let's first maybe have a look at the left-hand side, how it performs in terms of the set vertex position. So this is the resolution with respect to the original Atlas implementation. As you can see, we have pretty good agreement here also on the micrometer level. It of course depends on the bin width you choose, and it has not been optimized yet at all. And as always, it will be a trade-off between resolution and speed. But what you can see on the right-hand side is where I plot the speed up with respect to the original Atlas implementation versus the number of tracks in your event. And you can see that we have a significant, really great speed up with respect to the original implementation. So in the order of between 10 and 30 times faster than the original implementation. And as you can see, the relative speed ups also get greater for higher track multiplicities. So this approach will most likely be pretty well suitable for high pileup events where you have a high track multiplicity. So all these approaches and everything I've shown you so far were rather classical approaches to vertexing. And since we now have fully functional and working vertexing in place in ACTS, we also started exploring a little bit the field of machine learning for vertexing. I'd like to talk about this a little bit on the next slides. So our goal is to construct a vertex finding algorithm that is based on a neural network. And the idea is to learn a track representation in some embedding space in such a way that similar tracks, where similar means that these tracks originated from the same vertex, are close in this embedding space. So we want to have a neural network, and once we put in a track together with its covariance matrix, we want to have a representation in embedding space so that another track that is also coming from the same vertex is extremely close in this embedding space. And neural network architecture for this track embedding could look like the following, where on the left-hand side we have our input, which is the parity parameters plus some flattened covariance matrix entries. Then we have some hidden layers, which are also concatenated for some better gradient flow. And on the right-hand side, we have our track representation output, in this case, a 10-dimensional embedding space. The question is now, of course, how to find or learn such a representation. And our approach here is to use a so-called Siamese neural network, which you can see on the left-hand side. And what you do here is you use this track embedding network I just showed you. You use actually one single instance of this network twice, sharing weights and working in parallel. And then you would train the Siamese neural network by giving as an input always a pair of tracks, so always two tracks. And if these two tracks came from the same vertex, this network should output a score of 1. And if the tracks are coming from different vertices, it should output a score of 0. So I've done some training. So I've trained such a network so far only on ACTS smeared truth tracks so far, on pileup 60 events. And I got a score accuracy of roughly 90%. And what I can do now with this, with these scores, is I can construct an adjacency matrix. If you have a look at the matrix on the right-hand side, each row and each column in this matrix represents a single track. So, for example, in the first row, the second entry, the 0.96, would mean that the first track and the second track in this event would be compatible to come from the same vertex by 96%. And what you can see is we have this really nice block structure, and you could basically, in this simple case already, just by eye, cluster this matrix into vertices. Problems arise if we have these non-zero interconnections here between the blocks. But what you can, of course, do, the most naive approach basically is to take this adjacency matrix and cut all values below a certain threshold. So what you can see on the right-hand side, on the lower right, this block, what I did, I just took adjacency matrices and cut it everywhere, all values below 0.5. And what you can see is that this approach is indeed able to reconstruct vertices. So this seems to be working. However, problems, we still have some problems. Or what about the cases where these interconnections are stronger than the ones I showed you above, or cases where it gets a little bit more difficult? And our idea, and this is already some kind of outlook, is to consider this entire problem as some kind of graph problem, where the nodes in the graphs represent the tracks and the edges between the nodes similarity scores, meaning that in this case, this orange block in the adjacency matrix would correspond to this densely connected subgraph on the left-hand side, the blue block to the one on the right-hand side, and so on. And then you could just use some graph clustering algorithm to actually cluster these matrices to vertices. And this would then also allow for clustering more difficult cases, like the one here where you have stronger interconnections, where you could still somehow by eye see that this might be two vertices, But with this really naive approach, there would be no way to actually construct two vertices out of this. And of course, since we're dealing with a graph problem, we will for sure also be looking at alternative approaches like graph neural networks for getting these adjacency matrices, these graphs in the first place. This is something we will for sure be looking at in the future. All right, this brings me to my summary and outlook. So in the ACTS software, we have an MT-capable vertexing suite, which is written in modern C++. The ACTS adaptive multi-vertex finder will most likely be used in Atlas Run 3 for the primary vertex reconstruction. Various vertexing R&D is ongoing, both classical and machine learning R&D, where graph clustering and GNN approaches are in a quite early stage, but look pretty promising. Of course, lots of work need to be done here, and we are also looking forward to extend this to use full ACTS record tracks with the Atlas ATK description in the future. Thank you.
Yeah, thank you, Bastian, for this very interesting talk. And I see already hands raising. David.
Yeah, hello. Simple question. So the adjacency matrix, are you computing the full matrix, which can be quite large, few hundreds times few hundreds at maximum?
Exactly. So what I've been doing here is, so first of all, the tracks are ordered in set 0. And then I would just specify a certain set window, and within this set window, I would then run the neural network on the track path to create this adjacency matrix. Yeah.
Okay, makes sense.
Okay. Other questions? I also had the detail, I think on slide 6. I mean, I didn't quite understand what the Atlas baseline was, which you compared his, the results to. No, it was slide 7, sorry. What is the Atlas baseline here?
Yeah, so as I've already mentioned in the I can quickly go here in this slide under Vertex finders. You can see that we already have the Gaussian track density vertex finder in ACTS running, and this is basically the exact algorithm that Atlas implemented, which is based on the assumption that we have a continuous track density, and this is fully working in ACTS, and so this works pretty well. And this approach I took then and put it on the grid, right? And that's what I'm comparing against here. So the exact same. So
that's how you got the speed up. Okay.
Sorry?
That's how you got the speed up then. Exactly.
Okay.
Yeah. Well, it's replacing a PDF convolution with a histogram bin addition, right? Is that correct? A binned convolution.
Say it again, sorry?
So it basically replaces a proper convolution with or density estimation with a binned version.
Exactly, and yeah, basically, yes.
Okay, I think we should close that talk. Thanks again, Bastian, for the nice talk. If you could unshare, and the next